So my presentation today will be on basically an overview of Bhutan Space and Satellite Program. I think you've heard quite a lot about the different elements of the program from the various speakers here, and I'll try not to repeat many of the things that they've said, and I'll try to go quickly through some of the areas that have already been mentioned. So essentially my outline of the talk is talks about the vision, I think, and as the other speakers in the morning mentioned, this is the vision that has been set by His Majesty the King for harnessing space and space technologies for the benefit of the people of Bhutan. The second part I'd like to talk about is the orbital slots. This is actually the entry point for Bhutan into space activities. The third area is Bhutan 1, which was also touched upon earlier. It's Bhutan's first CubeSat that was sent into space. The fourth area that I'd like to touch upon is talking about Bhutan-India cooperation in space. This is an added dimension to our two countries' cooperation, and we are getting a lot of assistance from the government of India in furthering our own space aspirations. After that, I'll talk about several other activities that are going on. Many, I think, that you might have actually been involved in. And then finally, we have the concluding remarks. So in terms of the vision, this has been set by His Majesty, who we can consider as the founder for the space and satellite technology program in Bhutan. It's, as we mentioned, to utilize space resources and technologies for the benefit of Bhutan, and also to safeguard resources that have been allocated to Bhutan. The second goal is to inspire youth, like all of you, to become more interested in science, technology, engineering, and mathematics. The world is getting more and more technology driven, and as some of the speakers mentioned, I think if we don't keep up, there's a big danger that we could be left behind, and so it's very important for us to inspire our next generation to become more interested in these sort of activities. And the third is for Bhutan to participate in and contribute to humanity's space exploration efforts. We might be a small country, we might be starting out late in our journey in space, but there's still a lot that we can contribute to the world. We are part of the humanity here, and so we need to think about what the future holds for humanity and how we as a small country can contribute to that also. So in terms of the benefits of space research and technology, this was touched upon earlier by the science secretary from ISRO. Basically, global communications, where you have satellite telephones, now you have satellite internet, those sorts of things. Then we have broadcast satellite television. Then we have the positioning and navigation systems, the GPS systems, the Google Maps that you use is all based on this. Weather forecasts to make predictions about what the weather is going to be like. Environmental observations. And then technology development, since the environment in space is so harsh and so challenging, I think many of the technologies developed for space use is far, far ahead of the technologies that we actually use currently, and many of those come down as ripple effects and help us in developing technologies and using them back here on Earth when they become more cost effective. There's a lot of research also going on in the International Space Station, and a lot of exploration also taking place. And I guess one of the main reasons for the exploration is also to find out what lies beyond our own solar system. And also from a more practical point of view, you know, Earth is the only planet just that we humans occupy just now. And if you do have an extinction level event and a huge asteroid were to collide with Earth, that might be the end of the human race. And so this is one of the motivations for, I think, the interest of people in setting up lunar settlements, maybe settlements in Mars, and even in the search for exoplanets, so that we have alternative places that we can go to if something of that nature were to happen. So Our entry into space age actually should have begun in 1988. This is when the International Telecommunication Union, an orbital slot to Bhutan. So these orbital slots are actually slots where you can send up satellites. And these are essentially like real estate in space. And you can only send up a satellite if you have this space allocated by the International Telecommunication. So they are the regulators that give the approvals to different countries for using and it's a very rare commodity. There are actually about only 1,800 orbital slots that can be used. And with the expanding number of countries and the number of space agencies that are sending up satellites, this is becoming a very crowded space. And normally what happens is after the ITU, before the ITU allots this space to you, they do a lot of frequency coordination, because once you send a satellite up, you have to ensure that if there are other existing satellites, the signals that come from your satellite don't interfere with the signals from the other satellites that come. So in a sense, ITU is also looking at the equitable distribution of space facilities for all the countries, which is why they've allotted these orbital slots. And so 2 slots have been allotted to Bhutan. One was allotted in 1988, and the other was allotted in 2000. It was His Majesty who mentioned in 2016 that Bhutan has been allotted these 2 orbital slots and wanted to know what we were actually doing about it. And that was actually the first step that we took towards establishing space-related activities. The second thing that we are doing is also looking at the optimal utilization of these slots. So it's to try and see what we can do with these slots. One is that we could send up a satellite ourselves. The second is that we could lease these satellite orbital slots to other countries that might be interested in sending up satellites. Or the third alternative is that we could work in partnership with some of these countries to send satellites to these orbital slots. So in a sense, like I was saying, this is actually the start of our entry into the space age, when the ITU has actually allocated these 2 orbital slots to Bhutan. And it's only now that we are coming to realize how important it is for us. The second step in our move towards space is Bhutan 1. So while the Satellite Working Group and the Department of Telecom and Space was working on the orbital slots, we noticed that Kyushu Institute of Technology had sent out some information that they were organizing a BIRDS program. So the BIRDS program is essentially a master's project where they invite several different countries to form teams, and they actually build, design and launch the satellites with the help of Kyushu Institute of Technology. So this is where we had sent 4 of our engineers to design and build Bhutan's first satellite. And it was a very proud moment when it was launched on the 8th of August 2017. And when this was launched, Bhutan was around the 85th country in the world to launch a satellite. So that is quite a momentous thing for us. And we are amongst the first, in the first 50% of countries that have launched such a satellite. So I think that is something that is really good for our satellite program. And I'll not talk more about this, as Kiran from the Department of Telecom and Space has a separate talk on this. Simultaneously, while we were working on the space program, India itself was also looking at increasing bilateral cooperation with its neighbors in the SAARC countries, and they had announced that they would offer a satellite for the SAARC countries at the Kathmandu summit in 2014, and within a very rapid space of 3 years, I think they launched the South Asian satellite, and it is essentially a gift from India to the SAARC nations in pursuit of their own neighborhood first policy. And this is where we've been a big beneficiary from the government of India, and we'd like to thank them for their support to Bhutan in this area. Currently, we're using one transponder from the SARC satellite, but we are also in discussions with the government of India, and I think those discussions were initiated last year when Prime Minister Modi came to Bhutan, and we've requested for extra bandwidth from the SARC satellite, and they have given some very positive feedback about providing this additional bandwidth, and we are hopeful that we will get it very soon. So in terms of what the SARC satellite is actually used for, earlier BBS used to lease the bandwidth from other commercial companies, but now they have shifted to the SARC satellite, and so we have 2 BBS channels and 4 radio channels that are operating out of the South Asian satellite. It is also providing off-grid connectivity to 3 geogs in Thimphu. So this is one of the big advantages of satellite technology, you know, where our fiber optics can't reach and where internet connectivity is not possible through these sorts of technologies. Satellite makes it possible for us to reach each nook and corner of the country, and that's, I think, one of the biggest advantages of satellite technology. And in terms of use, I think for us, dealing with disaster-related issues is where we see a huge potential for use of satellite technology. We have VSAT terminals that have been set up in 20 dzongkhags and 60 geogs. So in case our telecommunication network goes down for any reason, we'll still have this backup facility through the satellite channels. We also use the satellite for backup international connectivity and domestic connectivity backup. So in all of this cooperation with the government of India, the Indian Space Research Organization, ISRO, is our partner, and we are very happy to have such a partner as ISRO, and as the speaker in the morning mentioned, they have such a long history. It's 50 years that they've been operating in this space area, and they are one of the premier space agencies in the world. As I mentioned, they have over 100 spacecraft missions. The Mangalyaan Mars orbiter was one of the big events in ISRO's history. They were the 4 and 1, just to remind myself that, you know, they were the 4th space agency in the world that was able to successfully launch Mars orbital mission. The 1 stands for that they were the first country in Asia to actually be able to successfully do that. So they've been very, very successful at what they're doing, and he mentioned, I think they've also created a record launching 104 satellites at one time. And of course, one of the big points about ISRO is that they're one of the most cost-effective space programs in the world, and he gave the example of the Mangalyaan mission that cost a little over 4 rupees per kilometer for the orbiter. So in terms of the specific support that we've been getting from ISRO, while the government of India had agreed to provide us services from the South Asian satellite, we did not have a ground station that could receive the signals from the satellite. So the government of India has been very generous to provide both the technical and human setting up and training people at DITT, and this was done through ISRO. And as the speaker in the morning mentioned, we are also now working towards joint development of a small. So the team that was actually involved in building the CubeSat will now be engaging with ISRO to build a much larger satellite, and the joint working group has been set up. There's a lot of discussions taking place with regard to finalization of the payload, and we are quite optimistic that things will start moving very quickly in this area also. The other area that we are looking for assistance from ISRO is with regard to high resolution satellite images, both for land use planning purposes and also for trying to get some time series data, high resolution images for our monitoring our glaciers in Bhutan. We had a big disaster in 1995 when we had the first glacial lake outburst flood. And so if you're able to monitor these sorts of things, then we can get a lot of advance warning in terms of these disasters that could be imminent, and a lot of safety measures could be taken. And so this is where we are engaging with them also to try and get more information from them. So this actually is a very big deal for Bhutan, starting space activities, because this offers a new dimension of cooperation between India and Bhutan, and we hope and expect that it will help to further deepen and strengthen the already very strong ties of friendship that exist between our two countries. And in terms of space agencies in other countries, besides ISRO, we are also looking at JAXA, which is the space agency from Japan, and JISTA, which is the space agency from Thailand. After this space initiative started, we've also had a lot of space programs. Last year, when we had the astronomers and scientists who had come to install the Panoptix telescope at the Royal Academy, we had the first talk on astronomy here in Thimphu, and there were a lot of people who attended, so it was very encouraging. We also have a lot of radio talk shows that we've started now at Kuzu on space and technology-related activities. And another very interesting activity is this search for exoplanets. Before I get into it, just as a background for how we got into this is that this is here again, we received guidance from His Majesty that maybe Bhutan should look at setting up a space observatory in Bhutan. We don't have any such facilities, and so this is where then we had invited some astronomers and scientists to come to Bhutan to see the feasibility of setting up such an observatory in Bhutan. And when they came to Bhutan, they said that yes, Bhutan does have very good conditions for setting up a space observatory. We are high up in the mountains, the environment is very clear, we have dark skies because the environment is not very polluted because of light around. And also another point that they made was that this space activities is not just confined to one country because it has the capabilities, but we need to try and distribute these sorts of activities across several countries, because when you're looking at the sky, there are some sections of the sky that some countries will not be able to see that other countries will be able to see. And so this is where there is an opportunity for Bhutan to actually participate in some of the global space activities that are taking place. And so this is where we've started on this activity also, and like I mentioned, that we might be a small country starting out late, but we are very interested in contributing to the world in terms of these sorts of activities. And the suggestion that the astronomers and scientists made was that maybe setting up an observatory in Bhutan, we could look at it from a rather medium to a long-term time scale, maybe 5 to 10 years, to see whether we want to set it up. And there would be people who would be interested in setting it up. But what they suggested was as a very short-term measure and to do something very quickly, they suggested that maybe we could go ahead with this Panoptix Telescope project. So essentially, the Panoptix project is looking for this transiting exoplanets. So, and as many of you know, exoplanets are planets that are beyond our solar system. And so this, the Panoptix telescopes actually helps identify these sorts of exoplanets. And these exoplanets are very interesting, as I mentioned earlier, and when I mentioned exploration, is that just in terms of human curiosity, in terms of learning what is out there in space, but also from a more practical point of view of in case we were to have some sort of disaster here on Earth, besides the Moon and Mars, these exoplanets would be other places that you would be looking for human habitation. And what they look for in these exoplanets is the habitable zone. I think they look at the star and the planet and see how far the planet is from the star, to see whether there's possibility of the planet having water, because water is one of the most important requirements for sustaining life. And since there are thousands and thousands of exoplanets, we are discovering more and more. And so as you discover these exoplanets, many of them will not have this habitable zone, but there might be a few out there that will have. And so this is where Bhutan is also getting engaged in this activity to try and identify these sorts of exoplanets, so that we are contributing to the humanity's quest for space exploration and human habitation in the future. So these are essentially citizen science projects, and we've set the 18th Panoptix Telescope was set up at Royal Academy. So you can see we are slowly moving up. We were the 85th country to send up a satellite. We were the 18th country to send up a telescope, and maybe some of you here will be the first to do something unique for Bhutan. So looking to set up 2 more of these Panoptix telescopes, maybe one in the south and one in the east. And like I mentioned, these are part of the global network, so they're just looking at basically a piece in the sky, and all that data is going to a central server and that is actually looking at, and all the data from all these telescopes will actually be integrated to see whether there are exoplanets in the area that we are looking at. Another very interesting activity that took place last year is the naming of an exoplanet. The International Astronomical Union celebrated its 100th year anniversary in 2019, and as part of its celebration, it gave the opportunity for all countries to name an exoplanet. So we had an exoplanet naming committee together with the Department of Telecommunication and Space and the Satellite Working Group and some other representatives also. And there was a competition that was held here in Bhutan. I hope many of you participated in that competition. And the Bhutanese name for the exoplanet that has been allocated for us, for the star HD 73534, it's Gaki, and for the planet HD 73534b, it's Drukyul. And the person who has the distinction of having named Bhutan's first exoplanet is a student in class 9 at Motitang High School. I think the 4 engineers that were able to go to QTech were able to source the financing through assistance that was provided from His Majesty's office. The CANSAT leadership training program was also possible because of the support that has come from His Majesty's office. And many of these activities have actually emanated from His Majesty's inspiration and guidance. So as a result of which, I guess so much has taken place in the last 4 years. Many milestones we've achieved, but this is just the beginning of the space program for us. It's been a big step for us to move in this direction, but I think everyone here is very, very enthusiastic about the space program. I think the government agencies are very excited about what they're doing, and I think it's creating a lot of awareness amongst the public. I think here we are very fortunate for schools that are close to Thimphu to be able to attend these sorts of seminars, but I think we need to reach out to other schools in other dzongkhags also and take this message that we need to become much more enthusiastic, excited, and develop more of a passion for this science, technology, engineering, mathematics, as the future is going to be driven by these sorts of activities. And in conclusion, I would like to say that it is people here in this room, I think, the students, teachers, different agencies that have this big opportunity to actually take forward the vision of His Majesty the King. The big momentum has been built up, so much support is there, and I think we all have to work hard to try and ensure that we fulfill the vision of His Majesty. Plus, thank you.
Okay, and we are running a bit short of time, so I'll try to be brief and quickly give you an overview of how we went about developing the first satellite of our country. And in the sessions in the morning, the launch session, and also Commander sir in the previous presentation has touched upon Bhutan 1 quite a number of times. So I tried not to repeat those things again, but give you an insight of what happened when we were actually building this satellite. So this is the outline of my presentation. I'll start with giving a brief background on what is BIRDS project, and then I'll talk about how we actually went about developing Bhutan 1. Then I'll talk about the ground station that we have here in MOIC campus, which we use to track our satellite on a daily basis, and then also give a brief status of what our satellite is doing currently. And then I will end by talking about the lean satellite concept. This was already mentioned earlier, BIRDS program or the BIRDS project. It's also called Joint Global Multi-Nations BIRDS project. So in short, it's BIRDS project. It was an initiative of Kyushu Institute of Technology in Japan. And the mission statement of this project, it reads something like this: by successfully building and operating the first satellite of the nation, make the first step toward indigenous space program at each country. So what this initiative does is it brings in, it was already mentioned, it brings in students from developing nations. And through this project, they give the hands-on experience to those students to build an actual satellite, launch it in space, and then operate it through the ground. So the BIRDS project kicked off with BIRDS 1 project. It was in October 2015. And as of now, the BIRDS 4 project is currently ongoing. So the students from Philippines, Paraguay, and Japan, they are working on developing a 1U CubeSat for their own countries. The project started in 2018, October. Then the satellites are expected to be launched later this year. Now, with that introduction, I will focus on Bhutan 1. And as you might already know that Bhutan 1 is a 1U CubeSat. So 1U, one unit, meaning that it has a dimension of 10 centimeter by 10 centimeter by a 10 centimeter cube. And again, you already know that there were 4 engineers part of this project, BIRDS 2 project, who worked on developing Bhutan 1, and all 4 of us were undergoing our master's course. And the primary objective, if I mention it here, it was to build capacity on how to develop a satellite. And if you look into the process, what are the different stages of developing a satellite. So once the project kicked off, we started consulting stakeholders and then conduct some feasibility study, and then we reached the milestone where we determine our missions. And once we have our missions determined, we start designing our circuits and then implement it in a breadboard, which we call it breadboard model. Then we finalize our preliminary design. And then after having our preliminary design ready, what we do is we go about building a prototype, and we call it engineering model. So once we have this engineering model, EM, ready, we put that model through a series of tests, and then we try to determine whether that satellite can survive the rocket launch and whether it can really operate in space or not. But if we feel that there are still a lot of changes needed, and in some cases we have to go on and build a second prototype, which is quite common in the satellite development process. So in our case, in BIRDS 2 case also, we had to go and build our second prototype, the EM2. And then after we had our EM2, we found that then our design was good enough to be sent to space. Then we went about building our flight model, which is the actual satellite which goes to space. So from kickoff of the project to having the satellite ready to be delivered to the launcher, in our case it was JAXA, the space agency of Japan, it took us about 18 months. So in the next slide, I've just captured few images of what those different stages look like. So this first image shows a breadboard model of one of the subsystems. So there were many similar kind of breadboard models for different subsystems, and we do some tests, integration tests, and see whether all of the subsystems are able to communicate with each other or not. Then once we finish that, we go about and build the first prototype, which was the engineering model 1. And like I mentioned earlier, we had to go and build our second prototype. So if you can look closely in these two images, you can see some visible differences. One being the antenna of the satellite. So in one we have patch antenna, the another one we have monopole antenna. But I'll not talk about the differences of patch antenna and monopole antenna. Maybe since most of the audiences are students, you can go back and try to research about what are those antennas. And then after we have our engineering model 2, we have our flight model, so which is the actual satellite which went to space. Again, here you can see some differences. Internally, it's basically the same, the EM2 and the flight model, but you can see externally there is a very significant difference, that being the solar panels. The flight models have solar cells on the side, but the engineering model does not have them. And the primary reason being, solar cells are very expensive, so we cannot afford to have solar cells on a model which is just going to sit there and not do anything. So that's why the solar cells are only attached on the flight model. But rest, if you look closely, they are mostly same. And internally, this is how our satellite looks like. Yes, on this side, you can see the CAD diagram. So before we built our satellite, when we start manufacturing our components, we have to do our design. We have to see whether the boats can fit in well. So here I have shown how the different boats are stacked upon each other. So we have a boat in the bottom, and this acts like a backbone of our satellite. So all of other boats, they are inserted on this boat on the bottom. We have connectors here, if you can see some black connectors here. So this is basically a excuse me, CAD diagram. I'll not talk about different boats in detail here, but if you look closely, this is the actual image of an actual satellite, how it looks on the inside. And this is the satellite which went in space, which is currently orbiting our Earth. Now talking about the mission, so Bhutan 1, the primary objective was to build our capacity and learn about how we develop a satellite. But doing so, it was not just building. After we launched the satellite, we also had to operate from the ground. So to do that, we had designed our satellite to execute certain functions on space. And one of it was an amateur payload. So there was a radio, a transmitter, and a receiver. What it did was receive the text message sent from ground and then broadcast it within its coverage area. And then we had a very small camera. This is a commercially available camera, very small one. It can capture images. So what we wanted to do was try and see if we can capture image of Earth from space. But the images that we get from this camera does not really give any specific information that can be used for maybe other activities. Then we also had a GPS chip. This was a newly designed GPS chip, and it had never been sent to space. So what we were trying was to have it in our satellite and send it to space and see if it can really operate or work in space. And similarly, we had other missions whereby we had magnetometer to measure intensity of the magnetic field of the Earth on orbit. And then satellite usually experiences a lot of radiation, effects from radiation. And such when satellite experiences radiation, it can lead to reset of the satellite, which is unintentional. So our satellite was also designed to take note of such events, and later this information could be used to determine how much of a satellite in that orbit experiences radiation effects. Now moving on, once we have our designs ready, once we have our boats manufactured, then we move on to the phase which we call as assembly, integration and testing. So here I have an image of Bert's room, what we call as a student room, where all the project members. So in Bert's 2 case, we had students from Philippines, Malaysia, Japan, and of course from Bhutan. All of us were, this was like our office space. We were sitting there, we were working. Whenever we don't have class, we will be in this room. Then here we built our breadboard models, then do some testing. But then when we move on to building the prototype, we do most of these activities in what we call as a clean room. Now, as the name suggests, this room is supposed to be cleaner than any ordinary room, because when the rooms might seem clean, but in the air there are very minute particles which we cannot see through our naked eye. So those particles can be quite harmful for the satellite when it's in space. But this room is maintained in such a way that it's much cleaner, and the components that we keep in this room can really survive the space conditions. And once we have our satellite assembled, we do some testing. We do that testing in the clean room itself, but there are some certain specific tests which we need to be conducted in very specific facilities. Like the first one we have is a thermal vacuum test. It is conducted in a chamber. There is a big chamber which can simulate the temperature conditions of space, because the temperature in this orbit and on the Earth is very different. So we need to see whether the satellite that we sent in space can really survive that sort of temperature variation or not. So if you look closer, this is how the satellites were arranged inside the chamber to conduct this test. And next one is the vibration test. This is again a very critical test because when the satellite is placed inside a rocket and when it is launched, the satellite experiences a lot of forces, and these forces are very huge. So we need to ensure that because of these forces, the satellite does not break on the way to space. Because if it does, and if some of the parts after it breaks off from the satellite, it comes out of its place, it can also affect the rocket itself. It might lead to the failure of the rocket launch itself. So that's why this test is quite important, and we need to ensure that satellite is safe and it can survive this the rocket launch. After we do all these tests and we determine that our satellite passes all the tests that we put it through, we deliver it to our launcher. So basically, for our case, JAXA was the agency responsible for launching our satellite. So our satellite was launched to ISS, and then from ISS it was released into the orbit. And I have a small short video here showing how the satellites were really released into the orbit. So if you can see there, the 3 satellites, Bhutan 1 from Bhutan, and then Maya 1 from Philippines, and UITM-SAT from Malaysia. So these 3 CubeSats were released together in the orbit from ISS. So this is how the satellite started orbiting our Earth, and this video was captured from the International Space Station. So since then, our Bhutan 1 has been orbiting Earth, and it has already been a year and a half. And every day from our ground station here in DITT, MOIC campus, we are tracking our satellite Bhutan 1 along with other satellites from the BIRDS project. And as of today, we have been receiving the beacon signal from the satellite. Beacon signal basically indicates whether the satellite is alive or not, and whether the satellite is operating at optimal level or not. So I'll discuss more about the beacon signal in the subsequent slides. And just as an information, our satellite also is part of what we call as a ground station network, Earth ground station network. Now, like I mentioned earlier, we have been receiving a beacon signal from the satellite on a daily basis. And what this beacon signal contains is firstly the temperature data of, oh no, not temperature, battery and voltage, voltage and current data. So this information is very critical for the operators on the ground, because once satellite is sent in space, we have no control over what it does and how it operates. But from the ground, the information that makes us know whether the satellite is in good health or not is this battery voltage and current. So here, if you can see the battery voltage of Bhutan 1, this data is for second half of last year, from July to December last year. So battery voltage throughout this period has been above 4 volts, and current has been oscillating around 0. So which is an indicator of good health, because a battery, if you see, it still has 4 volts, which means that there is enough battery, enough charge to operate the satellite. And then current, if you see, it has been oscillating within the 0. So sometimes it's positive, sometimes it's negative. And the reason for that is battery are charging when there is sunlight, and it's discharging when there is no sunlight. So that's why the battery current, it appears positive sometimes when it is discharging and negative when it's charging. But this basically indicates a good health of the satellite. And similarly, we also get temperature data from the satellite. So we get about 5 temperature sensor data, but I've just plotted data for 3 of the sensors, one being the battery temperature. So battery is very critical in satellite operation. The batteries that we have in our satellite, the temperature should not go below 0 degree. If it goes below 0 degree, the satellite battery starts degrading, and eventually the battery will stop functioning. Then, which basically means the satellite is dead. But if you can see here, the battery temperature has been mostly positive. The blue line, if you can see, it's mostly in the back. So battery temperature has been very optimal for our operation. But the next boat, which is closer to the external boat, if you can see here, it's experiencing a larger variation in temperature. Sometimes it's becoming hotter, sometimes it's becoming colder than the battery, because it's very closer to the outside. And then the back plane, the boat that is on the bottom of the satellite, as I showed earlier. So this is very close to the external boat. So it's almost like outside of the satellite. And if you can see there, this boat is mostly remaining colder than the other components. So these were some of the data that we're receiving from the satellite as of now. And like I mentioned earlier, our ground station also is a part of Earth's ground station network. So these are some of the countries who are part of the Earth's ground station network. So we have 15 members as of now. And today, currently, all of these ground stations are trying to track Earth's 2 satellites and Earth's 3 satellites. And here I've not mentioned Earth's 1 satellite, because Earth's 1 satellite have already re-entered Earth's atmosphere and disintegrated in atmosphere. So Earth's 1 satellite no longer exists, if I put it in simple form. But we are expecting Earth 4 satellites to be up there soon. And finally, this is my last slide. I'll talk about lean satellite concept mainly because the BERT program has adopted this approach. And what we do here is try to build satellite faster. So this was a very short animation that I created while I was in Japan. So what this animation shows is the facilities that we had for our satellite development, and how far those facilities were, how easy it was for us to access those facilities, and how much time were we spending moving around these facilities. So if you can see here at the end, so most of the facilities that we used while building our satellite, it was very close to each other. So it comes within the 30-meter radius. So there were 2 buildings, and all of the facilities were there within these 2 buildings. So we barely had to move out or go out of the college campus for the implementation of this satellite. Basically, the lean concept, the lean satellite concept is that we want to try and reduce the waste of waiting and moving. Because traditionally, whenever an agency starts building a satellite, what they do is there is a lot of time is spent, and they are very expensive. That's why for a small country like Bhutan, it seems impossible for us to venture into space technology. But now with such new technologies and new concepts coming up, it has become feasible even for a country like Bhutan to venture into the journey of space. So with that, I would like to end my presentation here. Thank you very much for listening.
On behalf of the Gross National Happiness Commission, I would like to extend my heartfelt gratitude to the Ministry of Information and Communications, especially the Department of IT and Telecom for including GNSC in this very important initiative. I'm really pleased to join the conversation today on space technology, not only to marvel about the next generation of technology, but also to accept and acknowledge that it is our responsibility to ensure that space technology is used for the good of all Bhutanese as His Majesty the King envisions. I'm sure that the space seminar today and the subsequent activities that have been planned for the rest of the week will take us on a journey to outer space, and that is amazing. But we must remember that we must journey back to Earth, because space technology is not only about sending rockets and astronauts to the outer space, but it's also about addressing issues and challenges that are important here on Earth, such as access to quality education and healthcare, and also to ensure food security. So my presentation today is mostly going to touch upon some of the development challenges that Bhutan is currently facing and how space technologies can be used to address these issues and challenges. Okay, so in terms of our social indicators, we have made tremendous progress, and these are some of the examples. So our life expectancy in 2005 was only 66.3 years old, but it has now increased to 70.2 years old in 2017. Households with access to clean water has increased to 99.5%, and 92% of the households have access to sanitation. In terms of our education, our net enrollment rate has increased to 98.8%, and our literacy rate has increased to 71.4%. And these are tremendous progress that we've made. However, we have issues. Okay. However, we still have issues. So if you look at the disaggregated figures, although we have done very well in our health indicators, we still have issues of inadequate nutrition facilities. So our stunting rate has increased to 21.2%, and 9% of our children are underweight. In terms of education, 3.2% of our children are out of school, and we have issues in ensuring that the healthcare and education facilities that we are providing are of quality. There's also other emerging issues, such as increasing incidences of mental health issues. We also have issues of increasing non-communicable diseases and also substance abuse. In terms of poverty and inequality, we have made a tremendous progress if you compare the data to 2007. So our current poverty rate is 8.2%. However, again, like if you look at the disaggregated figure, we have issues. So if you look at the urban poverty rate, it's only 0.78%, whereas rural poverty rate is 11.94%. And this gets worse because if you look at the Dzongkhoks with the lowest poverty rate, it's Thimphu and Paro. And if you compare that to Dzongkhoks such as Dagana and Shemgang, you see a huge disparity. Also in terms of our Gini coefficient, it has been gradually increasing. So we have issues of inequality and poverty that we need to tackle. In terms of Bhutan's economic performance, we have sustained an average growth rate of 7.5% over the last 3 decades. However, we must remember that our economy is single sector driven. So share of hydropower to GDP is the highest, whereas it has not really translated into generation of employment, especially for the youth. And we are struggling with limited structural transformation. So agriculture's share to GDP is the lowest, and this is a problem because majority of our workforce is employed under the agriculture sector. Likewise, we also have a narrow range of exports, and our export market there's an export market concentration, and more than 70% of our exports are going to India. So these are some of the economic issues that we have to address as well. In terms of economic vulnerability in climate change, as we all know, and some of the prior speakers have already touched upon it, so Bhutan is under the potential threat of glacial lake outburst floods. So we have 677 glaciers and 2,794 glacial lakes. And in the last 4 decades, we've had incidences of glacial lake outbursts. So we must address these issues as well. And obviously, I must say that GNHC is definitely not the expert on space technology. But with that being said, I would like to convey that there are so many examples of how space technologies are already being used all over the world to ensure sustainable socio-economic development. And in my subsequent slides, I will be giving you guys some examples of how space technology is making a difference in socio-economic development. So there are many space services that can benefit us, and I would like to focus on 3. First is the communication satellite. So most of these have already been covered by the previous speakers as well, so I'll just briefly go over them. The second is the Earth observation satellite. So these satellite images provide information on our human settlement patterns, agriculture land use. It also provides us information on temperature, ocean currents, snowfall and rainfall. Then we have the space spin-offs. So basically, space spin-offs are technologies that are invented to be used in space, but that they can also be transferred here on Earth to benefit us. So I noticed that there's a separate session on space spin-offs, so I won't delve much on it, but I would just like to give you an example of space spin-off, a technology that is being used. So one of the best examples would be the water filtration system that is being used by the astronauts in the International Space Station. So as you know that the water in space is limited because the astronauts there get shipments of water. So while the astronauts are waiting for the next shipment of water, basically they use the water filtration system to filtrate and recycle the water that they are using. So even their urine is being filtrated, and the technology that's used is of really high quality. So the water that is recycled is clean and as good as new. So these are some of the technology that was invented for use in space, but because these technologies are very effective. They have been brought down to Earth, and a lot of countries are already using these space technologies to ensure that they have clean and drinkable water. Okay, so just a few examples on Earth observation satellites. So, as I mentioned earlier, Earth observation satellites are basically used to provide you with information to understand what's happening around the environment, and it also enables you to make better decisions. So for example, satellite imagery through Earth observation shows agricultural land, and it can even provide farmers with information on when to add water to the crops, or when to put fertilizer, and even when to harvest the crops. And it also provides information such as the vegetation index, and it shows the productivity of the crop and also the productivity of the land that's being used to grow the crop. So as I mentioned earlier, we have the national key result areas and the sustainable development goals, and these indicators are very much linked to ensuring food and nutrition security and ending hunger. Okay. Another example of how Earth observation satellites are being used is in providing images that enable broad and efficient monitoring of water reservoir, water levels, and providing early warning of water shortages or flood. And this is extremely useful for Bhutan because, as I mentioned earlier, glacial lake outburst floods are a potential threat to Bhutan. And this contributes towards ensuring that our national key result area on ensuring sustainable water and SDG goal 6, which is clean water and sanitation, is achieved. Okay, so we all know that Earth observation satellites also discovered the hole in the ozone layer, and today it still remains a key to fight climate change. So Earth observation satellites, it enables monitoring of deforestation. It also measures pollution levels in the water bodies. It provides us with information on the status of ice caps and desertification, and enable early and immediate action to prevent these events, which helps us to achieve the national key result area on carbon neutrality, climate and disaster resilient Bhutan, and SDG goal of climate action. And towards SDG 15, which is to safeguard life on Earth, Earth observation satellites also helps in monitoring and protecting wildlife habitats by identifying indicators of impending development or destruction and alerting authorities to engage early. This is extremely useful for Bhutan in our effort to protect and monitor our wildlife in the parks and biological corridors. And then moving on to the second type of satellites, which is the communication satellites. So communication satellites is an excellent example of where we can get great benefits, because we can spread information through radio broadcast, internet and television all around the world, including remote and cut-off areas where infrastructure is limited. So this is particularly very useful in ensuring quality health and education accessibility. So an example would be someone in the rural area can connect to and derive benefits of the best doctors and specialists in a city maybe, through telemedicine, and likewise for education as well. These satellites ensure good health for the community, helping us achieve our NKRAs and SDG goals, and also education, especially in areas where infrastructure is limited. So these are some key examples that Bhutan can use to further our socio-economic development. And as we all know, the launch of Bhutan 1, as mentioned in the previous presentation, basically marked Bhutan's first step towards development of Bhutan's space science and technology program. And to further the initiative, there are some activities that have been planned under the 12th five-year plan, and these are as follows. So first, there's Space and Satellite Initiative, so basically to raise awareness and interest on space program. There's also activity to build 3U and 5U satellites. There's an activity to file for orbital slot, which was covered in the previous presentation as well. There's also a plan to launch a full-fledged satellite network for disaster communication. And there's an activity to draft space policy and regulation so that there's a legal provision in place. And finally, construction of satellite control building. So the overall budget for space program in the 12th five-year plan is niltrum 305 million. And this is just the beginning. As mentioned in the previous presentations, the potential and the opportunity to utilize and leverage space technology for socioeconomic development is enormous. And in the 12th five-year plan, the activities that's mentioned, that's just the beginning. So as we discuss space technologies for development, we must realize that there seems to be a role for every one of us here in this room, whether you are a policymaker or whether you are a implementer of one of the programs, or whether you are a student, there seems to be a role for every one of us. So even if you want to use if you're a technical person or a quantitative person who wants to use data to basically help improve people's life, there is a role for you. And we must remember that we can all be enabled by space, and in doing so, we must create opportunities for all Bhutanese to benefit from the space technologies as well as envisioned by His Majesty the King. And I would like to end by saying that we must bring together our skills and our imaginations to make us all space enabled and fulfill His Majesty's vision. I'm really excited to be a part of this dialogue and to join and contribute towards it, and I hope you are as well. Thank you.
So I'm here to actually talk on CanSat, and it's actually a type of, we'll get to that later, but anyway, CanSat is considered to be a project. It's a project-based learning for imparting space education. And it is very popular. It is becoming very popular in other parts of the world. And CanSat has made space education reach to the students and other non-space engineers. So in this talk, I'm going to give you what CanSat is and why is it very important, why it is important for space education, what is going around in the world regarding CanSat, and how we can use CanSat for imparting space education to the students. And then we'll also look at the end, what are the challenges we face, especially for educating students using CanSat for the space and space technology. So if you look at this picture, you probably might now get an idea about what is CanSat. Can you make out anything from this picture? Pictures? Can you? Yeah. So what can you make out of these pictures? You can see, what do you see? You see can, soft drink can, and then some electronics components. Yeah. So what these CanSat means is actually a satellite. It's actually a satellite which is of a size soft drink can. Have you seen soft drink cans? Isn't it? So this is a satellite which is built of a very small size, 350 ml size of can, and then as well as it weigh around 150 to 200 milligram. No, actually milligram. It's gram. All right. So it's a very small satellite, and especially this satellite is used for educating students about space science and technology. So this idea actually started in 1998 in one of these symposiums. And this idea was proposed by Professor Bob Twiggs. What he said was, all the universities, all the universities who are participating in building a satellite should build a small satellite, and it will be launched together in the space, just like you see in the picture. So every university in the world who are participating in building the CANSAT will build their own satellite, CANSAT, and then launch it in the space together. But this idea actually failed because of the cost of launch. And in the previous talks, you might have seen that launching is very costly affair. And because of these, the idea was dropped, and rather what this CANSAT idea was used for educating students rather than building a satellite and then launching it together in the space. Why not we use this for giving awareness, giving education to our young generation, which will be more helpful because this will generate more awareness. This will generate the brief idea, knowledge about the whole space project. So then onwards, this CANSAT was actually used in training students and policymakers in regards to space. So what is CANSAT? CANSAT is actually a simulation of a real satellite. So in CANSAT, what you do is you go through each and every process of satellite building. You must have already seen in the morning presentation by Mr. Kiran. You go through a lot of process to build the CANSAT, satellite, and this CANSAT actually help you go through all this process to build the satellite and make you learn how you build a satellite in a real life. All right, and this satellite CANSAT can be actually built in a very short duration, rather than taking years and years to build the satellite and imparting knowledge. Using CANSAT, what we can do is we can educate students within a short period of time how to build satellite. So in this CANSAT, we do the real mission, like taking the picture of the Earth, recording, video recording. We also take the measurements of the atmosphere. So everything can be done using CANSAT, and this will actually give you the real picture of how you go through the process you go through the development of satellite. And this also challenges you because CANSAT has to be built of a very small size. I told you earlier that the size of the CANSAT is 150 ml. 150 ml is very small, and then you have to fit all the components, parts into that small size container. So this challenges you. As a student, this challenges you to develop the skills of building the satellite. So that's why CANSAT has become very important all over the world to provide space education. So the first CANSAT was launched not actually in the space, in the orbit, but rather just for experiment. Launch up to like 4 kilometers in the atmosphere using the rockets, and these rockets were built by U.S. Amateur Rocket Group, called Aeropac, and they formed a collaboration called ARLIS. And during this ARLIS event, what universities do is they come together from all over the world. They come together in Nevada, in the US. They come together, and then there is a group of people who provide rocket, and with the help of this rocket, they experiment the satellite by launching these into the air about 4 kilometers. And while this satellite is being launched in the air, after reaching certain height, the rocket launches the CANSAT, and then the CANSAT then drops to the ground. And to deaccelerate, to slow down the drop of the CANSAT, students have to design, parachute and glider in order for the CANSAT to slow down when it is dropping to the surface of the Earth. So this really gives you the experience, real-life experience of building the satellite and experimenting with the satellite when it is falling down on the Earth from a certain height. So this is quite costly, especially if the university and the schools are, from developing countries. So there are other alternatives which you can actually use it for launching a satellite. So you can launch satellite using helium balloons. You can also use, going to a certain height and then dropping your CANSAT. So there are different methods that you can use to actually launch your satellite. So the CANSAT was really popular because of the competition. There are two types of competition that is organized in different universities. Even high schools also participate in the CANSAT competition. So the first competition is called conventional CANSAT, which is where you build the satellite, and then the real competition is only to gather some of the collect some of the data while the satellite is falling to the Earth. Once the CANSAT has been launched through one of the methods, it takes 10 to 20 minutes to drop to the surface of the Earth. So during this period, what students can do is do the experimenting of gathering data, like for example, image capturing, videos. You can also read atmospheric pressures, air temperatures, and all this during this 20 minutes of the drop. And these help students to actually experiment the real satellite development and testing. And there is another type of CANSAT competition called open CANSAT, and in the open CANSAT there is no restriction of the size. The conventional, there is a restriction of 350 ml size of your can, whereas in the open class there is no competition, there is no restriction. So your CANSAT size has to be somehow it will be bigger than the conventional CANSAT. And at the beginning, when the satellite was launched with the help of these Aeropac, this Aeropac rocket it can hold actually 3 CANSATs, but if it is an open class CANSAT, then it can only hold to one size CANSAT. So that's why when you're building open size CANSAT, you have to think about the open size CANS has to fill into this, should be fit into the rocket. So that is the only restriction that is there when you're designing the open class CANSAT. So I'm not going to get details, technical details, get into the technical details of the CANSAT, because it's quite same as developing a satellite, because you have to fit a component, all the components that is there in the satellite. For example, EPS, electrical power system. You also have to have command and data handling subsystem. You also have to have mission subsystem, the sensors and everything. You also have to have a communication subsystem where communication happens between the components as well as between the CANSAT and the ground station. So all these components has to be there with, and you will be actually building it in the CANSAT. But I'm not going to go in details about this all. But I'll just talk about what is the importance of CANSAT in education. So CANSAT actually gives you a hands-on training of the whole cycle of satellite development. In the real life satellite development, it will take years and years to build a satellite. For example, 4 of our space engineers took 2 years, I think, almost 2 years to build a satellite and then launch it in the space. But if you would like to know how CANSAT is built within short period of time, so this CANSAT will help you. So CANSAT can be built within 1 year or even less than 1 year. So that is beauty of these CANSAT, which will help educating students regarding the space. Then other good thing about CANSAT is you can use all engineering education, starting from the basic physics. You'll be able to use all this knowledge in building CANSAT. So that is another good thing about CANSAT. And other thing is when you are building CANSAT, you utilize project management knowledge. So you get to utilize project management. You'll be able to utilize system engineering. So all these knowledge are made into practice when you're building this CANSAT. So these are the points which actually helps or why people find this CANSAT to be very useful in universities and schools. The other important point is that the whole CANSAT, like I said, can be completed within very short period of time, and then it costs less compared to building bigger satellite like CubeSat and the bigger satellites which are built takes a lot of time and money. But if you want just an education how the satellites is built, so this is very cheaper alternative. And even though the CANSAT is very small, but everything fits into the CANSAT. Every component, like I said, is built into the CANSAT, so it covers the real satellite development process. And other good thing about this is you can also experiment. You can also test your CANSAT, just like doing testing for your satellite. Remember in the morning session, you do vibration test, you do vacuum test, you do the lot of elements, exposure in the universe. So such kind of testing can also be done on a CANSAT. Especially vibration test is really carried out in CANSAT because you need to launch your CANSAT during the CANSAT competition. So same kind of test which has been done on the real satellite is also done using CANSAT. So like I said in the earliest slide, there are types of CANSATs, and this CANSAT is based on the type of competitions that is held around the world. So if you look at this slide, there are 2 types of competition. One is called combat competition and the other one is telemetry. What happens in the combat competition is you build a CANSAT, you compete with the other groups from different schools and university, and What you do in the combat competition is once you launch your CanSat, you have to target your CanSat to certain location. So probably on the ground you put a flag, and then once you launch your satellite using rocket or a helium balloon, or maybe climbing to a tall structure and then dropping your CanSat from there, and then while your CanSat is falling towards the ground, you can steer it using a parachute or a glider. And then once it is on the ground, you can also use rover. You can just guide your CanSat to move towards the target that is on the ground. So that is called combat competitions. So you aim towards the target. Whereas telemetry competition, what you do is you just take a normal, readings from the environments, or you just take an image, or you capture a video of Earth surface. So that's the basic competition, but real challenging competition is the combat competition, because in that you put in practice all the knowledge. Like I said, the knowledge of electrical engineering, electronics engineering, even civil engineering, because civil engineering you need to focus on the structure, as well as you also make use of programming, coding. Coding is the most important in the CanSat, because once you have the hardware, if you do not comment, if you do not program the brain of the CanSat or any satellite, nothing is going to do by your satellite. So you need to do the programming. So that's why I focus more on the programming side, because programming is the most important part in any electronic device. Okay. So in the CanSat, what you learn is mission creation and sequence generation. So remember in the morning talks there were something regarding missions and all this. So in CanSat also you learn to define the mission, what your CanSat is going to do. So you'll be doing mission creation and sequence generation. You will be also designing the satellite architecture. So how many components you require in your satellite, what are the subsystems that are required. So you will be designing the whole CanSat yourself. You will be also doing system analysis. For example, how much power you need for your satellite. Especially the power consumption by the components determines what kind of power source you need to put in place in your satellite. So that kind of analysis will also be done. You'll be also integrating the subsystems and fabricating it. You also go through all this development process. Remember that in the morning class now you have breadboard model, then engineering model, a flight model. So you do all this in the CanSat as well. Then overall project management knowledge will be utilized as well. You also do this assembling, integrating, and then testing of the whole satellite that you have built. As well as you do the field test and experiment with your CanSat by going to a launch site, and then once it is launched in the air, so you read or you collect, or you record the data on your CanSat, or send the telemetry to the ground station. So CanSat can be imparted in the different levels. You can, you can be provided training for just assembling a kit with a fixed mission, then ground test, and launching experiment. Or you will be given to create your own mission. You will be asked to buy subsystem components. As well as then you do all these testings, ground testings, and launch experimentation. So there are different levels of trainings that are provided using CanSat. And each level will give different understanding, different level of education to the students. Then there is a type of CanSat that is come out of the real actual the initial idea of CanSat. This has been, born out of the initial idea, and this was developed by one of the professor in Japan from Nihon University, and this is called Haptasat, and what this Haptasat does is it provides trainings to all kind of users, not only students but even policymakers. Policymakers can also go through this training to understand what are the requirements, what are the components, what we can do with the satellite. So this Haptasat is very good training kits that we can use for training our students and policymakers. And this Haptasat consists of, again, just like in the real satellite Nalu, all the functions, okay? Especially if I may be specific, in this Haptasat we have 6 functions and 6 primary subsystems. So all these layers that you see are different subsystems of the satellite, and you get to build this satellite yourself, hands-on training. And you can build this satellite, working satellite, within short period of time. Actually, this training is given in 10 days or 6 days, depending on the level of learning that you would like to do. And this is very good way of imparting space education to our students and space engineers.
Thank you.
Well, Argus Panoptix is a many-eyed Greek giant in Greek mythology. And now you must be wondering what it has to do with our project, Project Panoptix. Well, the name for Project Panoptix was actually taken as a backronym from Argus Panoptix. And what we do and what this robot can do is similar to what Argus Panoptix does. Our robot can see back and forth 360 degrees in night sky. Now, in our context, Panoptix is an acronym for Panoptic Astronomical Networked Observatories for Public Transiting Exoplanet Survey. And as a few of the previous speakers mentioned, that it is a citizen science project, and we aim in making it easier for anyone in the world to build a robotic telescope which is capable of detecting transiting planets. Now, the thing about our project is we have an open source data, which means anyone can access our data. And we highly encourage other groups and people like you to use our data, hardware and software in order to address other scientific questions. Scientific questions can be questions related to black hole. It can be questions related to other galaxies or our neighboring galaxy, Andromeda galaxy. And of course, we are in search for an intelligent life somewhere in the universe. And we aim in searching for the reason why we exist. And we also want to build a worldwide network of astronomers and planet hunters to come up together, and we also want to build a worldwide network of automated cameras which is capable of detecting a large fraction of sky, because one unit cannot observe all the sky in 24 hours. The trend has to be passed on to other groups or other units. We have a simple design. Our unit is made up of a camera box, a mount, and a computer control system, and it is cost efficient. And by that, we also want to involve schools and amateur scientists in all aspects of science, starting from data collection to data analysis. Now, when I mentioned the word exoplanet for a few times, how many of you here had a thought on this thing? Or have a thought on this guy, a little green man? Now, you must be knowing what an exoplanet is. Still, exoplanets are the planets which are outside our solar system, which does not belong to our sun. It is outside our sun and beyond Earth. And this is an image of the first exoplanet that was discovered. The name of the planet is PSR 1257+12a. And it was discovered by two radio astronomers, and it was found orbiting a pulsar. A pulsar is not a star, it's remnants of supernova. Now, I want you all to take a close look at this image. Can anyone see where our Earth is? If not, let me zoom in for you. Now, can you see where our Earth is? Yes or no? Well, our Earth is here. It's really tiny to be seen. Now, you can imagine how it would look like to look from our closest star, Alpha Centauri. So this is one of the challenges that we face while detecting exoplanets. Most of the time, the planets that we detect are planets which are of size of Jupiter and Super Jupiter or Saturn. So, because the planet is small in size, they are not able to cause a blockage in luminosity of the star. That's why we are finding it hard and difficult to find planet like Earth. So it would be a habitable planet like Earth. And one of the challenges is technical problem. This is a recent image where we faced with challenges with some wiring connections. So these are some challenges, and while solving these challenges, we get to learn new things. That's the beauty of science. And we never can trust technology, and it's unpredictable. The third challenge that we face is light pollution, which causes challenge and difficulty in seeing the stars clearly. Now, I want all of you to guess a number in your mind. How many stars will there be in an area of a thumb if you just put up a thumb in the night sky? So how many stars will there be in that area? Any guesses? If you have thought of a number, you can stand up and speak. Any guess? Well, more than that.
15 million.
Less than that. Any other guesses? Less than that. Well, actually, there will be 10,000 stars in an area of our thumb. And there are 100 billion stars in our galaxy. And in our universe, there are 200 billion galaxies. Now you can wonder how many stars there will be in our universe. Till date, we have discovered 500 solar systems, and they have been confirmed. And We have around 4,000 exoplanets that has been discovered and confirmed, but 3,000 more have been discovered, but they are not yet confirmed. Now the question is, how do we actually detect exoplanets? In our case, we use two methods: radial velocity or Doppler spectroscopy and transit method. And here's a visual on both of these methods. To elaborate more on radial velocity, we observe the frequency of light from the star and luminosity of the star. Whenever an object or a planet orbits around a star, it causes the star to rotate because of the gravity of that object. And this causes rotation of star, which astronomers mostly refer to as interstellar wobble. We also study the velocity at which the planet is orbiting. The star is orbiting in order to get more information on planet and more information on star. And we study frequency of light, which hereby I mean light color, change in color. So whenever star moves away from our Earth, it causes redshift, and when it comes nearer to Earth, it causes blue shift. If these changes happen frequently in a period of time, then we can assume that there's an exoplanet over there. And this transit method, the first image here is actually our sun, and the transit is caused by our moon. This image is just here to give you an idea about what transit is. So the second image is the main thing that we really care about. Whenever an object passes over a star, it will cause drop in the luminosity of the star. So when we plot a graph using some programming language, then this graph looks like whenever an object passes through. So this graph is what astronomers refer to as a light curve. So we use this method in order to detect planets. And this is a sample image from a Panoptix unit. We borrowed an image from Panoptix unit 13. Till date, we haven't been able to fully operate our unit, but we are going to start observation soon. So this is actually what it looks like from a Panoptix telescope. And this image is image of Andromeda galaxy. So now talking about the process. While building this telescope, we were divided into 3 teams, and we had to go on a rotational basis, and we had to visit all 3 stations on daily basis. Team A worked on site planning, so they were most of the time making site better and effective for the telescope to be installed. Team B worked in assembling the robotic telescope, and they worked with some trainers, and we could assemble it. And Team C was working on learning how to use a visual telescope and how to use softwares like Stellarium for space observation. This is some snapshots when we were introduced to the materials that were required for building the unit. And we worked in our class, so we made one of our class as laboratory, and we worked the entire time there. We also hosted some star and moon parties at night, which I mean space observation, night sky observation. And we use visual telescope in order to look at planets like Saturn, Jupiter, and Moon. And here are some images. This image is not really clear because it was taken from smartphone, and the image below Moon is actually an image of Jupiter. When we looked from visual telescope, it was really clear. We could see the bands of Jupiter, but here you are not able to see. And these 4 objects here are moons of Jupiter. And we spent a quite of time observing the space. We used to stay late till 11 p.m. observing the sky. And we also had space talks and astronomy classes given by the astronomers and trainers. And this is the real team who came to teach us how to assemble the unit and how to deploy the unit. Now, this is the forum where we communicate with other people who are also involved in making the unit. We address our issues and we try to get solutions from other people. And we also give them some solutions to their problem. And you can also go to this website and go to the community forum and ask questions related to Panoptix. So I want all of you to visit this site one day. And now, finally, what the future is going to look like. We are going to develop a machine learning software which is capable of detecting exoplanet and which is automated, so which doesn't require a human to stand over there the entire night collecting data. This can be done by machine, which is artificial intelligence. And we would like to involve app development team in order to come up with an app which gives frequent recent images that is taken from our observations using the unit. And we could send missions from Bhutan with using the data from Panoptix unit for exploration of exoplanet. And 3 units will be installed in Bhutan soon. Thank you.
I came here to deliver a talk on how to convince young people to be interested, to take an interest in astronomy. But then listening to young Ugyen from the Royal Academy made me realize that I might as well go home now, because your enthusiasm shines brightly and in your presentation, so well done. To start with my presentation today, before I begin, I'd like to share a fun fact that my boss actually pointed out to me. He says that in Dzongkha, the word tip, astrologer, actually means, if you break it down, Tsi is math. So an astrologer is actually a math whiz. So it's interesting that in our culture, astronomy, because astrology has something to do with space, so astronomy and math has been connected in our culture. So just a fun fact, nothing to do with my presentation. Kuzangpo, my name is Deepika. I work for the Royal Office for Media of His Majesty's Secretariat. I studied science in high school and undergraduate, but I became a sort of writer, and that's what my job now entails. So even though I manage a Facebook page called Space Club, and I host a show called Space Break on Kuzu, both of which are to do with outer space, I have to admit that I felt a little out of place in this seminar. This is the Milky Way galaxy, by the way. I wasn't that good in physics in school. I never thought about becoming an engineer. And I dropped maths in class 12. So when Yishe, our bright young satellite engineer, who's one of the organizers of this event, told me that I should be one of the speakers here, I have to confess I wasn't too keen. I thought, that this is not my vocation. I don't know the big stuff about outer space or astronomy, and I wouldn't have anything meaningful or substantial to contribute to this very exciting event and conversation that you're having today. This is just an aside, because you might be curious. This is the Horsehead Nebula as photographed by the Hubble telescope. But I wanted to be a part of this event. in some way. So I gave it some thought, and I realized that even as a layperson, I do have something that I can contribute to this event. And this is Saturn. Ugyen already showed this picture. This is Saturn as photographed by Cassini. And in this picture, Saturn is actually right in front of the sun, so it's eclipsing the sun. Very beautiful picture. As I said, I wanted to be a part of this event. And the reason for that was my enthusiasm. The whole reason why I have a Facebook page and a radio show dedicated to space is because I'm deeply interested in this subject. This was brought about by a topic that in our social studies textbook when I was in class 5. I had this life-changing moment when I was in school in Rinjin, and one day in class, as we were learning about outer space in social studies, the topic was the sun and our sun. And that day in class, we learned that the sun was really a star made of hydrogen and helium. It's a burning ball of gas and plasma. And we learned that the sun has a lifespan. So the sun was born maybe 4.5 billion years ago from a massive collection of dust. So it became a ball of fire. And given its size, scientists think that it is pretty much middle-aged. So in the next 5 billion years or so, it's going to die. As it does, it's going to expand and become a red giant. And then finally, it's going to collapse into a white dwarf. And when it expands, it's going to engulf the Earth. This is what I learned when I was in class 5. My world was shattered. I had no idea what 1 billion years might be. I remember that there was a stunned silence in the classroom, and our teacher assured us that by the time this happens, we all will be long dead and gone. But still, the idea that there are things out there beyond our control, and that one day everyone's going to die, that the human race will not go on, was devastating. And within that realization, something else also occurred to me. I wouldn't have been able to put it in words back then, but I had this overwhelming sense of our smallness and helplessness, that no matter what we did on Earth, things will go on as if none of it mattered out there in space. It was as if suddenly the universe in all of its glory and mystery had opened up to me. This is an amazing picture of galaxies seen through the Hubble telescope, also shared by Ugyen. The size of what is actually fitting into this picture is mind-boggling. So I realized that the world was so much bigger than my classroom, my friends, my family, and my little life. It was giddying and fascinating, and I couldn't stop thinking about it for days and days. Back then, we didn't have the internet or mobile phones with internet, if you can believe it. So I had to go to the Jigmedor Jiwangchu Public Library to satisfy my curiosity, and I did what you'd just go to your phone, Google app, and do a quick search. I had to go through shelves of books, but finally I found a beautiful book in the library with pictures of the planets and the moon, of the Earth hanging in the lunar sky, looking icy blue and marbly and beautiful. I remember being most taken by a picture of Jupiter with swirly orange bands across it, half obscured in darkness, where it faced away from the sun. It was beautiful. Did I mention that everything was so beautiful? That's Jupiter. And that was when I fell in love. I would always look up at night and shiver, and a shiver would run down my spine when I thought about how the light from the stars that I was looking at takes years and years, hundreds, maybe even thousands of years to reach us. What looks like the brightest star in the sky is actually Jupiter sometimes, with its beautiful bands of swirling color. That people had looked through telescopes and seen a ring around Saturn, that the bright star on the horizon on some evenings is actually Venus, which is so hot that spacecraft sent from Earth have melted away in minutes inside Venus's, as it got to Venus's surface. I realized that we are part of a galaxy. And back then, the night skies in Thimphu were dark enough for me to see this river of light, the Milky Way galaxy across the sky. As the years went by, I learned about asteroids and comets. I learned to identify constellations and look for meteor showers and eclipses. I discovered Carl Sagan's philosophical lessons, and the poetic beauty of the universe continued to amaze me. It's been a very fulfilling experience. I feel lucky to have had this in my life growing up. I use the love metaphor because it's been like that, bursts of joy now and again. Like the time New Horizons finally took a high-resolution picture of Pluto and you could finally see the planet for the first time clearly. Or the blue sunsets of Mars, this one, as photographed by the Curiosity rover. And I'm very keen to share all of this with you. I understand why some people have this instinct to share their religion, you know. They want to spread their religion because they feel so strongly about it. I give my nephews and nieces books about the universe and share with them my favorite documentaries on space. It's so easy to experience this happiness, really. All you have to do is know a few facts and find out things. There's so many fun things out there to learn about. And it's a lot of fun. So the Facebook page and the radio show that I have are extensions of that urge to share with others what has given me so much happiness over the years. And for me, it's been enough to know and to learn and see pictures and get excited. I feel like these are reasons enough to be what I call a space nut. This is Venus, by the way. But I work for His Majesty's Secretariat, as I mentioned earlier. And I'm very fortunate because my job gives me many opportunities to listen to His Majesty during audiences to students and teachers like today, and different groups of people. And the side effect of having listened to so many of His Majesty's addresses is, it's like if you read a lot of books, you can't help but learn a lot of things, and I think maybe get a little bit smarter, you know. Similarly, when you listen to His Majesty, you can't help but start thinking about bigger things, things beyond our own little life and everyday existence. You start thinking about the country, about nation building, what it really means, what legacies are that we need to leave behind for those who come after us. And these are things that we should think about because it gives our lives meaning and purpose. And this is Mars. So that's another reason to be a space nut. When I was growing up, when I was in school 20 years ago or so, no one told me that this could be a career option. I thought that to be an astronaut, you had to be American. I had to depend on the meager, outdated books in the public library to learn new things. But you have all the knowledge that humanity has ever discovered, accessible in a couple of swipes in your pockets, right? And right now in your pockets. There are so many opportunities for you. Events like this, the many things that have been described in different presentations since the morning today. All of them are designed to encourage you to succeed. All of us are rooting for you. And I want to join the voices to tell you that it is possible to become a scientist, to excel not only in Bhutan but elsewhere, to discover new things and make history. It's possible and it's worthwhile. This is a Curiosity rover on Mars. All the pictures are from NASA, by the way. So it's worthwhile to be a space nut and to dream of a career as a space scientist. Because when you try to find answers to the big questions, you invariably find answers to the small problems. When you figure out how to travel to Mars faster and more cheaply, You improve transportation as a whole. When you find a limitless source of energy to power these travels, you find better energy alternatives for us right here on Earth. When you figure out how to communicate better with whoever you've sent to Mars, you improve communication for us on Earth. It's time for us to become pioneers and discoverers. It's time for Bhutanese to be leaders in innovation and participate in the technological revolution as contributors, not just consumers. That's what His Majesty said in the morning today. We have to think about how we can contribute to technology and not just look at others' technology and think of how we can use it, right? And the Bhutanese who are going to be part of this revolution is you, the young people of Bhutan. It's your time to take your place in the history of technological innovation and discovery. And this is a space elevator in Mars. It doesn't exist yet. It's an idea, and this is from a documentary called Wanderers, which I highly recommend everyone should watch. All of this being part of technology and contributing to the world in this way, this is what His Majesty has been saying in a lot of places, including during the National Day address, and whenever His Majesty grants audiences to young people like you. I want to share a quote from one of His Majesty's address, which inspires me personally very much. I quote, "Climb higher on the shoulders of past achievements. Your task is not to fill old shoes or follow a well-trodden path, but to forge a new road leading towards a brighter future." So I hope you'll start thinking of yourselves in this light as those who will forge a new road leading ahead. In your own way, using your own various talents and skills, your hard work and determination. And this, by the way, is Pluto as photographed by the New Horizons. So I see myself in this light too. I don't think it's too late for me to do my bit. I think of my place in this whole story as that of someone who can help create enthusiasm and encourage people like you. They say that those who can't teach, and that's not to knock teachers at all. In this world of limitless information, teachers don't have to teach facts anymore. You can get that anywhere. But what those who take on the role of teachers can do is create that hunger for learning, that enthusiasm that will help you power through even the most boring and hard parts of learning, because you want to get to that light at the end. And that's the Earth, by the way. If you can't tell, that thing that looks like a shoe is probably Italy. Once, an Oxford professor of math, Marcus du Sautoy, came to Bhutan to talk about mathematics. He was talking about how interesting and amazing maths actually is. And someone from the audience asked him, since Bhutanese children find it very difficult to learn maths is very difficult for us, what can teachers do to make it easy? I really liked what Marcus had to say in reply. He said, sometimes maths is difficult. There's no way to make complicated things easy just like that. But what we can do is to help make it so interesting that children are willing to work hard and put in a lot of effort to figure out the difficult stuff. It's like learning music, he said. You don't teach someone notes after notes and expect them to keep working without inspiration. First, you let them listen to some songs. You tell them, if you learn your notes, this is what you'll end up creating, something beautiful and magical. So when students have to learn their basics, the notes, they have the power of the song in their mind, and they know what they're working for. They're willing to put in all the hard work and effort into learning the notes. It's the same with maths, and it's the same with other sciences. And this is Mercury. So I'm trying to get people excited about space, to get people to see the big and beautiful things, understand all the exciting possibilities that are out there. And I've been taking advantage of whatever platforms I get the chance to use, like this seminar and my radio show and the Facebook page. It's not a lot, but I hope that it'll be a droplet in the ocean. We need other droplets, and I want to ask you to join me. Space Break, the show on Kuzu, has been airing for nearly a year now. We took a couple of breaks in between because sometimes we're too busy doing our own jobs, regular jobs. But I'm planning to end the current hiatus before the end of this month and start the show again with a friend to make it more interesting to listen to. Because on the radio, I can't show you fun pictures and distract you. It usually airs on Thursdays at 5 p.m. Space Club Bhutan, the Facebook page, has been in existence for maybe 1 year, maybe half a year. At the moment, it's just a Facebook page with around 800 people following it. It started out as a place where I could communicate with some of the listeners of the show and share some pictures and interesting updates in the world of astronomy. The two listeners of my show and I have very robust discussions on there. That was a joke, by the way. I hope I have more than two listeners on the show. This is a picture of Jupiter as photographed from the South Pole. My intention for my Facebook page has always been to build a community of people with similar interests. And I think it's time now to step up and make it more of a club than simply a Facebook page. And what I mean by that is that we'll need some new members. I hope that some of you will want to join. Maybe when those of you who live outside of Thimphu go back to your Dzongkhags, you can start your own chapters of the club in your schools. As members, we can organize talks, help spread the word about events like this, maybe organize some of our own. Get together to watch eclipses and meteor showers, create spaces to share our photography and thoughts, organize volunteers to engage with younger children, organize movie screenings. Maybe we can get DOIM to buy us a couple of telescopes so that we can get together to look at the craters of the moon or Saturn's rings. I'm sure that whoever wants to join in will have dozens of great ideas about what we can do. Recently I just talked to the members of the Tech Force, Bhutan Tech Force, and they're going to talk. They're going to give a presentation afterwards. I'm sure you'll find it very exciting. Maybe we can have them in the fold and encourage other people also to do interesting projects like the one that they're working on. Maybe you can organize competitions. So there's lots of things that we can do with this Space Club. The idea is to create a vibrant community of space nuts who will encourage each other and help make everything more exciting for everyone else, and push our future astronomers and space scientists forward into their bright future. This is Io, by the way, one of Jupiter's moons. And the blue stuff that you see on top, I don't know how to use the pointer, is actually a volcano, because Io is highly volcanic. So one of the reasons that I agreed to be here today is to use this platform to reach out to you, especially those of you who will win the telescope from the quiz and join us to help build Space Club Bhutan. I say us because I already have a second member of the club, Ishe. For now, please go and find the Facebook page and follow it if you want to be part of the club, and we'll figure out what to do from there, and we'll share information on what's next on that page. This is Saturn's moon Enceladus, which has ice volcanoes, geysers actually. And like I said before, I feel like I'm preaching to the choir when I try to generate interest about space in this group, because all of you are probably here because you are already interested. So what I'd like to ask you to do is, when you go back, spread the word, be my missionaries, and tell your friends, get your friends and family and your younger siblings and your juniors in school excited about all of this, because, as I said, it's worthwhile. Lastly, I hope that all of you, especially the younger members of the audience, remember to look up at the night sky once in a while, whenever you have the chance, to marvel at the universe above us, because it's all very exciting. Thank you for listening to my talk today and not falling asleep, or at least falling asleep discreetly so that I didn't notice. And thank you to MOIC for having me. Thank you.
Good morning. First of all, I would like to thank DITT for organizing such event, and I would also like to thank Ashimishe for inviting us to talk on our project called Near Space Data Collection System. Today, on behalf of Bhutan Tech Force, I would like to talk to you about this topic, which we are working from last 1 month. First of all, myself, I'm Thimphu, and I'm the team president, and I look after all the engineering works. And we have Sonam Topke, he's a team manager as well as our spokesperson. And we have our youngest member as our past manager, he's Gelwang Penjor. And we have our team fabricator, Sonam Hindrup. And we have our team co-programmer, Kinga Jamso. So, what is Near Space Data Collection System? Near Space Data Collection System is a technique of sending a weather balloon with scientific payloads on board to the near space to collect necessary information for various purposes. So here's our rough concept of our Near Space Data Collection System. There will be 3 main parts, which are weather balloon, parachute, and payload. So we will be releasing this to the altitude of 65,000 to 130,000 feet above the ground, which is commonly referred as near space. And that area is between Armstrong limit and Kármán line, which is so high that no human can survive without wearing pressurizing suit. But low enough that there is still a small drag on satellite, and it creates dynamic lift to the aircraft if they travel fast enough. So now I will be talking about our parts. And first of all, it's a weather balloon. Weather balloon is a balloon which is commonly made up of latex materials, and it is filled up with helium and hydrogen. So due to their weight, it lifts the payload, and it's estimated to climb around minimum of 20 kilometers above the ground. And the second part is parachute. I hope you all know what exactly parachute is. Parachute is a device that slows down the motion of an object through an atmosphere by creating a drag force against the object. So this will bring back our payload safely to the Earth surface. So it is commonly made up of nylon. And the third and the most important part of our Near Space Data Collection System will be the payload. So what our payload contains? Our payload contains some electronic equipments like APR, which stands for Automatic Package Reporting System, and we have GCB receivers, solar panel, batteries, camera, microcontrollers, and sensors. Then this will help us to record data after reaching to stratosphere and bring back to us for various purposes. So what exactly our Near Space Data Collection System does? So here the weather balloon will carry our payload with some, as I told, sensors and microcontroller on board to the stratosphere, and then after reaching a certain altitude, it will start recording all the necessary data like temperature, humidity, air pressure, altitude, GPS location, and we can also calculate wind directions and wind speed from this data. What can we do with our Near Space Data Collection System? So we can use our Near Space Data Collection System for various purposes, like to monitor weather and atmosphere condition, planetary research, engineering, education, pollution monitoring, photography, videography, and we can also study about our ice glaciers, and yeah, we are also sending for fun. So here's an example of data that we will be getting from our payload called sounding. So as the balloon rises up, we will be paying a closer attention to the temperature and humidity. The red line shows the air temperature and green shows the dew point, which is actually humidity. The difference between that two lines tell us where the air is saturated and where the air is dry. So as we all know, temperatures tend to decrease when altitude increases. But it's interesting to note that if we go really high and enter stratosphere once, the temperatures tend to increase again and it gets warmer as we go higher. So I can say that our near space data collection system would be the hybrid of satellite and rocket in a simple form. It is so simple that even a single person can launch it. We just need to fill up the balloon properly with the proper conditions, and we need to select a proper launching site and put some sensors and microcontrollers on board. And yeah, just release in the air. Balloon will take the payload to the stratosphere, and the payload will start collecting data. Parachute will bring back the payload safely, and we can go and collect the data. So if it is only US National Weather Station sends 70,000 of payload weather balloon in a year, generally 2 to 3 times in a day, which is part of global radiosonic network. And this will help us to help weather station around the globe to forecast weather accurately. So this method of reaching to stratosphere is so cost effective that most of the people call this project as poor man's space project. So different payload is sent to the stratosphere for different purposes. Like I'm going to show you some name of payload which is commonly sent by NASA, Google, and ESA. These are radiosonic, ozonosonic, ravensonic, transosonic, and pylon. So these are, if I explain briefly about this all payload, radiosonics are usually made to measure air temperature, pressure, humidity, and altitude. And ozonosonic is made to study the layer of ozone layers and to monitor ozone layers. And ravensonics are measured to predict wind directions and wind speed. And transosonics are made to stay longer durations, like 1 to 2 months in a stratosphere by giving a data to the weather station. A balloon or a pilot balloon is usually used by airports around the globe to measure the height of clouds. So we have been working for long duration in robotics, and now I think Bhutan Tech Force are ready to take next level challenge. So I think now it's Bhutan Tech Force mission to near space. Thank you.
As you all can see here, hydro rocket. I just want to relate hydro rocket with STEM education. How can I just directly take a topic as hydro rocket and then relate it? I can relate hydro rocket with the original rocket in reality, in real life, how it flies, how it works, and then what's the pure mechanism of a rocket. So if I begin with hydro rocket, I would firstly show you about the vocabularies. So first of all, I will go with center of pressure. It is that point in a body where overall pressure acts. Secondly, thrust is the reaction force applied opposite to the direction of action force or the pressure applied. Next, drag is the resistance to the motion of an object when it moves through a medium. Propellant, a substance that gives in thrust to the rocket engine. And lastly, the payload, carrying capacity of the launch vehicle in terms of weight. Rocket. Now, why rocket? Why space seminar? Because rocket it's fascinating, right? It's totally fascinating how it goes against the gravity of the Earth, how it reaches out of the atmosphere, and how it works in the space. So rocket is an aircraft which obtains its thrust from rocket engine, which basically uses Newton's third law of motion as its basic principle of flight. And it carries its own fuel or propellant and oxidizers for the production of exhaust gas. So if I tell you about rocket itself defines it's a high-tech technology, but if I have to bring it down in a very simple term or in a ground level, I would define it in only 3 categories. I would firstly say the main body of rocket. Secondly, I will talk about the propellant. And thirdly, the payload. So the main body, why main body? The aerodynamic shape of the rocket or the aerodynamic structure helps the rocket to give a thrust or to reduce its resistance or the drag. Secondly, the propellant. With the help of the propellant that it carries and the oxidizer that it carries, it gains its thrust to propel itself. And lastly, the payload. The things that it carries for its operation or for its main work to do when it goes out of the space. These are different types of rockets, namely V2, R7, Saturn V, Space Shuttle, Ariane 5, Delta 4, Proton, CZ to F. In this all, I've just showed you about the length of the rockets. But within this, if I have to show, just look at Saturn V. It has multiple nozzles. It also has multiple stages. And same with the other rockets. They are meant for their own purposes. Next, the application of rocket. Rocket can be used in evacuation, city evacuation. Have you all seen that fighter jet? They all use this city evacuation during the emergency cases. Next, they use rocket are being used in missiles. Thirdly, they are used in launch vehicles. They are also used in satellites. When satellite reaches to the outer space, for the direction to be given to the satellite, thrusters are used. Thrusters are basically the rocket science behind that. And also in astronauts' pressurized suit. So if I go with hydrorocket, why hydrorocket now? Can you just think of it? Like, why hydrorocket? Why did I just select hydrorocket? Why not sugar rockets or rockets propelled by PVC? Yes, it's cheap. One factor is cheap. Secondly, I would say it's a very easy concept using the same principle of rocket, all right? And hydrorocket, as you can see in the PPT out there, hydrorocket is a model rocket which uses the water as its propellant. So out here, what we have done is we insert water inside, all right, inside the bottle, and then we apply pressure on that. When that pressure pushes the water downwards, it produces a thrust whereby the bottle propels up. So it's basically the Newton's third law of motion, right, guys? Okay, so if I start with the parts of hydrorocket, I would also divide it into 3 parts. Firstly, the nose cone. Nose cone is the first part of the rocket or the model hydrorocket which touches or cuts the air. Secondly, main body. Main body, this part. From here, this is the nozzle part, this is the end part of a bottle. So what happens is that the empty part of this is used to store compressed air. This part is around 1/3 by volume to store water. And this is the main part where the main thing happens. Lastly, main thing I will be talking about it later on, but then lastly, the last part of hydrorocket would be fins. Fins is basically used to give stability to the hydrorocket. All right. Now if I start with elements used for a hydrorocket, these are the elements. There are 6 elements that I have used in making a hydrorocket model. So firstly, fins. I have just said it earlier. Fins helps the rocket to fly straight. Whichever direction, whichever angle it is placed, it is fins, they help hydrorocket to just propel itself in one particular direction. Secondly, landing system. Landing system, there are so many different types of landing system, but why do we need landing system? Why do we need landing system? Anyone? All right, anyways, I'm here to tell about that only. Landing system, we are making a model with such a dedication. We want to make it work. But what if it goes up, but then comes down with more acceleration and gets broken? That's the most disheartening part. So obviously we need a landing system so that we can prevent that damage. So basically in this hydrorocket, I have used parachute, a simple parachute made from garbage plastics as its landing system. Launcher. And why launcher? Every rocket needs a launcher, right? So launcher, I've made for this hydrorocket with the PVC pipe so that it won't burst out. It can have its, it can hold that pressure. So that's why I have used PVC pipe for the launcher. So it helps launcher, it basically helps in holding and launching the rocket. Next comes the bottle, PET bottle. I've used PET bottle. And PET bottles are basically the carbonated soft drink bottles, right? Why do you think I've used this PET bottle? Why not other bottles like the high density plastic water bottles and all? Anyone? 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 No one. Sorry?
Because it's lighter.
Okay, one factor is that. Another one? Any other? Recycling also. But then the most important factor is that plastic bottle, this carbonated soft drink bottle can hold up to 120 to 130 psi of pressure. So that's the main factor. Like I need to push that water which is being inserted inside with such a great force so that my hydrorocket model can just go up to it may cross 200 feet. So that's why I need a carbonated soft drink bottle. All right, next comes the pressurized gas. Pressurized gas, how can I just get a pressurized gas inside a bottle? I can just get it by using a foot pump or a bicycle pump, which you all have seen, maybe, and the nozzle. Now comes the main part, nozzle. In this case, the regular carbonated soft drink bottle have 22 mm dia of nozzle. All right, I've used this because when the surface area of the nozzle is big, there will be not much of a difference in pressure, but the efficiency of the hydrorocket model will be more. And there are many other bottles which have less than 22 mm of dia, up to 9 mm of dia also. They have great pressures, but efficiency is just almost zero. So out here I have used the open nozzle, and the nozzle which have dia less than of 22 mm, they are known as stricted nozzles. Next comes the operation, the main thing in hydrorocket. So I fill the bottle filled with water, roughly around 1/3 of the volume, total volume of the bottle. Then I have connected the pressure pump with the pressure valve, which is being placed in the launcher that I have made in PVC pipe. Then I gradually increased the pressure inside the bottle up to 30 to 40 psi. So as you can see here, in this thing, this is a pure bottle. So when there is a space kept here, whenever the pressure goes up, it pushes the water down, and that thing makes the bottle to rise up, to propel up. So it's basically something that we can see in rockets, right? Now, next, I would like to show you the real demonstration of what I have done in my project. My friend is just putting his pump inside. He's pressurizing the bottle. I've already inserted the water. I'm just pulling the holder that I have kept it there to hold, right? It goes up. It goes up. How does it goes up? Just have a closer look. That's the force our water gives out. And for the landing system, you can just see it right now. And that's the parachute that I have made out there, installed it there, so that my model won't be getting any damage. And that's my model. Nextly, now the reason behind why I showed this hydro rocket in front of you all, just to show you what STEM education basically does. STEM education is something, it's a module education that relates or that helps us to understand the theories in our education system to the real life, what can I say, real life, day-to-day things that we do, all right? What I have shown out here is STEM, S-T-E-M. S-T-E-M, science, technology, engineering, and mathematics. This is the only thing that I have shown here. But if I had demonstrated here in front of you all, or if I had given anybody out here in the audience a chance to make it with the hands-on skills, that becomes STEM. That is with the additional of arts, all right? So STEM education is basically an approach of learning using science, technology, engineering, mathematics as an art of doing things, or as an art of getting access to the guiding point. STEM uses core subjects combined with design concepts, philosophies, and teaching methodologies that interest middle and higher school students. I have just mentioned middle and higher school students because middle and higher, they have a capacity of thinking. Whenever you see something, you'll be like, okay, this is a thing, but how can I change it? How can I make it? How can I just do what is being existed? So I'm basically thinking about middle and higher school students. The benefits of STEM education would basically be expose students to the creative process. You will be having a creative mind of doing things. You may see something, a technology, but you want to make it in your capacity. So that increases your creative process of your brain. Secondly comes, it increases the critical thinking. With critical thinking comes unique way of solving problems. Then it gives all students hands-on learning experience, encourage students to explore STEM fields. So with this, I just want to tell everyone that just take your 15 minutes back and think, when I said I want to relate STEM education, you could have just thought, okay, this guy is going to talk about STEM education. But what I'm going to tell about STEM education, it's something theory. And I'm pretty sure that 90% of the audience out here doesn't like theory. That's the thing. But then, if you had just thought in your mind, just two questions, what are we going to learn and what will I be learning? So that's the only two questions that STEM education teaches you. You don't have to worry about your marks, you don't have to worry about what your future job would be. But STEM education, it helps you to know like where you stand, what do you know and what you have learned. So I want to encourage everyone by promoting this STEM education in Bhutan. So I'm still planning if I can get help from my junior friends like Ugain, some Sonam and Tech Force. If I get help from them, I'm ready to introduce this STEM education in Bhutan as well, since I'm being trained in Aviaton Automation's LLP as a STEM educator. Thank you.
First of all, let's discuss what is a moon base. Well, as the name might suggest, the moon base is divided into two main parts. Firstly, it is a base. And by base, I don't mean just we go to the moon and build one house. No. By a base, I'm trying to say that we can build a settlement there. A complete settlement with its own economy, its own food source, and its own people. Secondly, I want this to be completely based on the moon. I don't want our moon base to have to rely on humans from Earth going there, no. Now we're gonna have the lunatics, the lunar ticks from the moon run everything from there. So now we've discussed what a moon base is. Why would I do this? Oh, look at this crazy man standing in front of us. He wants to build a moon base when there are no houses here on Earth. Well, there's an important reason we want to build a moon base, and it's one I'll touch on later. But first, just to get you an idea of what we're dealing with, there are three main reasons we want to build a moon base. Firstly, a moon base can give us access to a lot of resources. Secondly, the moon base can give us access to lots of space for human settlement. And the third one, well, the third one's a secret. I'm going to tell you later. So now we have all these new pioneers, these new geniuses, talking about building bases on other planets. Elon Musk. So, why do we want to build one on the moon? Not Mars, not Mercury, not Venus, the moon. Why? Well, there are a couple of reasons for this. Firstly, the moon is the closest celestial body to Earth. Having a distance of only 384,000 kilometers away from us, it's something that we have before reached in less than 3 days. This was back in 1969. We're in 2020 now. We can beat that record easily. Secondly, the moon has a lot of resources. Research conducted by NASA has confirmed that the moon has platinum, silver, traces of gold, and aluminum, to the point where the moon has been theorized to have a core made of pure platinum. That could be worth 500 quintillion US dollars in today's economy. To give you a sense of scale, the world's whole economy right now is roughly 130 trillion. The moon's entire resource base is almost 400 times what we have here on Earth. So now we've discussed why we want to live on the moon, we've discussed all of that, but now we're on Earth, we're not on the moon. So how are we gonna get to the moon? Well, currently, the method of propulsion we have is something like this. This is gonna be our rocket, okay? And the way we move right now is that we try blowing on the rocket. We basically have fuel, either solid or liquid, that we burn. And then it goes in one direction and forces the rocket to move. But there's a more interesting way, actually, because this kind of method uses a lot of fuel, it's very heavy, it's bad for our environment. But there's a method here, and it's actually quite surprising. It's something I never thought of. In 2017, NASA confirmed that this piece of paper right here, this piece of paper, when I shine my flashlight on it, this is a flashlight, apparently the paper actually moves. We can't see this, obviously, my flashlight is very weak, but research conducted by NASA has found that with strong enough lasers, strong enough flashlight, right? If you can focus the light energy we have and put it on one direction, we can make the paper move very, very, very fast. How fast, you ask? Well, that's 3 into 10 to the power 7 meters per second, 1/10 of the speed of light. To give you a sense of scale, that means that the previous mission to Mars took us 3 days. If we can research and make this photonic propulsion, which is basically fancy wording for light propulsion, if we can make this work, we can make it to the moon in, any guesses? How long do you think we'll take to get to the moon with this new propulsion? Any guesses? Any guesses from the audience? It doesn't matter. 10 seconds. Let that settle in. We can make it to the moon in 10 seconds. So now we've discussed how we're gonna get there. So now, happy-go-lucky, we're now the second people on Earth to walk on the moon. We do not have houses. What a shame. Time to start building. There are two main ways we're gonna start building moon bases. The first one is temporary living in moon caves. We can't immediately start building the moment we get to the moon, right? But there are already little houses that people have already left for us. Asteroids, that is. So in these craters, which can be almost 30 kilometers deep, humans can settle there and they'll be safe, first of all, from the temperature, secondly, from the radiation, and thirdly, from anything that might fall on the moon's surface. And then slowly, slowly, as we have more people and we get more time, we can actually start building on the moon using the moon. The lunar dust on the moon has all the materials required to make cement, first of all, and it's even better than just taking Earth materials because the dust on the moon is naturally resistant to radiation. We don't have to worry of getting cancer and dying. So now we've made it to the moon. Look at that, we have houses, we've made it through the whole problem of being on Earth. Oh no, we've run out of food and there's no oxygen anywhere to be found. What a shame. Well, let's discuss first of all the more important thing, oxygen. How do we make oxygen once we're on the moon? Well, it's interesting. But the lunar regolith, which is basically a layer of dirt slightly below the main layer of dirt on the moon, contains oxygen. We can catalyze this oxygen using a small device, almost just as small as this laptop here. And with that, we can generate oxygen for 50 people. Just something like this. We can generate oxygen for more than 50 people. Then, as we go on, we need to start making food, right? Food and then water. Well, for that, we've discovered that in 2018, SpaceX and Elon Musk and his group had discovered that you can grow plants in outer space. Actually, you can grow plants so well on the moon, even better than space, because the moon has a gravity. It's not very strong. It's 1/6 of the Earth's, and that allows the plants to grow taller. Not only does it allow the plants to grow taller, if you can find a way to water it and make the soil possible, right? Make all the soil, all the other minerals available, we can have yields up to 10 times what we have on Earth. It's amazing. Not only can we use the moon as a place to settle, we can use the moon as a place to make our food, make our agriculture. So now you want to sit back, relax. You got food, you got drinks, you're trying to turn on the TV, and look, you can't turn on the TV, there's no energy. So how are we going to make energy once we get to the moon? Well, the most easy answer, and one almost everybody uses, is the solar panel. Specifically, a solar sail. We're not going to put solar panels on the moon because we need to use that, but instead we can have big solar panels flying through space. In like the satellites that were discussed the entire day, we can have solar panels that are flying through space and that they can be very thin and then generate electricity for us. Also, something to consider in the future, far, far future, is something called a Dyson sphere. So a Dyson sphere is a very new concept to anybody. There's not a lot of research done on this either. But basically, a Dyson sphere is like a group of mirrors, okay? So we're basically putting a bunch of mirrors around the sun, and what the Dyson sphere will do is it'll accumulate all that sunlight, all those strong sun rays, and put them onto small, small pads. Like we can have one solar panel here, and we can have the whole energy of the sun directed towards that one solar panel. This can give us immense amount of energy. How much energy? Well, 5,000 times what Earth is using every hour. We can generate that much electricity. And with that much, finally, let's try discussing exactly the effects on Earth. I touched on it that time, but I didn't really elaborate, and I left a secret as well. Firstly, the moon is full of resources, as I've mentioned. Platinum, titanium, aluminum, gold, all of these are very rich, very expensive, but more importantly, it allows us to build more complex robotics. With such metals at our disposal, we can build more robots, more communication chambers, more rockets, right? And such resources can also help put countries that are currently in poverty and help raise their standard of living, right? There's a socio-economic factor here. We can help people be happier. Secondly, the moon is an excellent place for settlements. Projections by the UN have discovered that the world's population, right now, it's roughly 7 billion. It's going to be 8 billion by 2025. That's 5 years from now. And eventually, because you keep hearing all the time, and it's a very big threat, global warming, extinction, all of these things are happening on Earth. Here's a funny fact. The moon cannot be warmed. There's no atmosphere for us to warm. There's no animals for us to kill, and there's nothing that we can actually mess up there, right? So even though Earth is bigger than the moon, the Earth has an estimated capacity of 20 billion people because of all the water, all the other things we have to consider. The moon has a capacity of 150 billion people. We can support a lot more people on the moon. But now it's the final reason, and before I say it, I think it's time we travel back a bit. The year is 1969. Mankind has taken its first step on the moon, right? 1969. Buzz Aldrin, Neil Armstrong, first men on the moon. And for those that small second, that 1 hour as he took the first step and said the famous words, "It's one small step for a man, a giant leap for mankind." Was there any war on Earth? Was anyone disagreeing? I think in the last century, that was the one moment that we were all the most united. We were all most at one. No one was arguing with each other. Everyone was marveling at the fact that us, a bunch of stupid apes, had managed to make it to a moon so far away, something so big, something so majestic. And isn't that what we all want? If we, instead of just taking a step on the moon, maybe we can live on the moon, right? We can live on the moon and imagine how peaceful everything will be, even if it's for just the shortest second. There will be no war. Once we make it to the moon, it'll be easy from there. We can make it to Mars, we can make it to different galaxies. All those beautiful galaxies that we saw that time, we can go there. We can visit all those planets. Once we make it to the moon, we should be able to make it everywhere. And once we can make it everywhere, everyone here can be whoever they want to be. Why? There's infinite resources, we have infinite time, we have infinite peace, infinite happiness. And well, we're an intelligent species, aren't we? Isn't that exactly what we want? As my late role model would have said, Stephen Hawking, intelligence is the ability to adapt to change. The world is changing fast. Humans may go extinct very soon. Either we're going to kill ourselves because of global warming, there's going to be a nuclear war, or a big asteroid's just going to come up and end our whole species. But if we can move to the moon, if we can prove to the little God up there that we too can travel to different planets, we too can make it to big, big things, we would have achieved forever. Our species would become infinity. That's why I think we need to make it to the moon. That's why we need a moon base. Because that moon is our door to infinity. Thank you.
My talk is on spin-offs of space exploration. So since there are a lot of young students here, some of the young people may not know what the meaning of spin-off is. So before I get into my lecture, I would like to quickly explain what spin-off means. So spin-off is usually used to denote some outcome or byproduct from some other things. For instance, here, when there is a lot of investment in the space exploration, and there is some unintended, good outcome that can be used for other purpose in our life. Usually, some products or services that has come out from space exploration. Now, we use this a lot even in businesses. Business na bewachin. Now, let us take DGPC for instance. All of you in the DGPC, Duke Green Power Corporation Limited, one of the biggest companies in Bhutan. And DGPC has given rise to two smaller companies. One is called Bhutan Hydropower Services Limited. I think it is in Gelefu. They do repairing of turbines and all that. So it is an example of a spin-off of DGPC. Then there is another company called Bhutan Automation Services Limited. That's also a spin-off from DGPC. So spin-off is used in that kind of connotation, Seshunila. So there are a lot of spin-offs that has come out from the investment in the space exploration. So I will go through that. But so this is the outline of my presentation. I will not go through all. And probably you have heard of this one. I couldn't come in the daytime to listen to other speakers because I had some other important meetings. I had a board meeting. So I don't know if this picture came up in any of the talks today, but this pale blue dot was taken by Voyager 1 on 14th February 1990. And can you see the dot there? This is our Earth. This is the actual picture of Earth taken by the Voyager 1 in 1990, 14th February, exactly about how many years, 30 years ago. So, it's very humbling. It's just a, just a dot in the whole universe that we are living in. And in the whole scheme of things, our Earth is just a speck of dust. It's so humbling. This is the only home that we have, and it's just a speck of dust in the whole universe. So when I think of that, it's an amazing feeling and also very humbling. So from that perspective, I have interest in space. But today, my talk is on the spin-offs. Now, frankly speaking, I'm not really well versed in the topics of space. But because I was given this topic, so I did research on that for more than half a day last Sunday. And then I prepared my presentation session. But it was very good. So I came to learn a lot of things while preparing for the presentation. So there are a lot of spin-offs that have come out from the space technology, space exploration. So maybe before I quickly showed you the screen, but you might have seen it. But are there anybody here who knows some of the interesting spin-offs that have come out from the space exploration? One of the most interesting one I feel is that we always use is, I think, the GPS, Global Positioning System, has been improved upon a lot. I think even originally it came out of the space exploration investment, but it has been improved upon a lot through a lot of research that has been carried out by many space agencies around the world, most notably by NASA. I think on this planet Earth, NASA probably is the most advanced research organization when it comes to space. So I will be referring to NASA a lot. But that is not to discount that other countries don't have their space programs. Many countries around the world now have the space programs. In the 21st century, space is the new frontier in Mevola. So as Sonam Tenzin pointed out, in 1969, we were able to land a rocket on the moon. But now, how much technology has developed after that much? So space exploration has improved by that much. So these are some of the popular ones. There are lots. NASA says that there are around 2,000 spin-offs from their investment in the space exploration. 2,000. Only 5 I've highlighted here, but around 2,000, and many in the field of environment and medical and healthcare. Space exploration help. So these are some of the data on the spin-offs. This is taken from a OECD publication. So there are different sectors: manufacturing and consumer products, then transportation and public safety, environment and resource management. Into various fields, there are lots and lots of spin-offs that have come out from the investment in the space exploration. And those of you, the young students as well as others who are interested in the space economy, the business side of space. So I think this is the Ngagi Research Peodalu most definitive guide the anime. It is available online as well. So the space economy in figures published last year by OECD. So this is not just confined to NASA IMEVA. There are lots of publications from NASA talking only about the things that NASA has done. But this one is more comprehensive from mainly the OECD countries, but also from countries around the world. So space, it's an investment, and for the investment there has to be some return. So what is the return like? So this is covered in this kind of publication, OECD. So you can look it up, space economy in figures. It's a 2019 report. And OECD has brought about 3 publications in the past. So this is the latest publication. So space economy side, if you are able to read this, you will become quite thorough about space economics. Then I'll not dwell a lot. So there are a lot of graphs. So these books, this is from the book that I just mentioned. So overall economy, the impact from the literature review study there can be lots of different ways to calculate this, but this publication has looked at a lot of literature reviews, and they found that overall economy, the space has a contribution, positive contribution of 11.6%, and then this is broken down into different sectors nalu impact karibe duga. Now, when you look at this, you should understand from this perspective as well. This is also actually, supported by the space organizations. Now, these space agencies are funded by what? The taxpayers' money. So when it is funded by the taxpayers' money, they have to also show that this is having a positive impact, that the money is not going down the drain. So but it is not exaggerated. I think they are showing the real things, that the impact has been made, say. So these are some of the examples. Again, if you are interested, you can request for the presentation. They can share with you. I'll not go through one by one. I'm the last speaker, and I don't want to hold you from going home soon. So these are some of the examples. So the reason why I'm highlighting this is that it's not just confined to NASA, Italy, then there is the research organization in France. From there are a lot of spin-offs. Now, when it comes to NASA specifically, NASA Gidi, every year they bring out an annual report for the publication called spin-off. And this report also you can read online. Every year, 1976 le goes to the Dato Sinse, every year they publish this report, spin-off. And in this annual report, they highlight the different applications from the technology developed by NASA. So spin-off 1999, then 1976 le Dato Sinse, they are saying that they have brought about around 2,000 spin-offs, 2,000 different applications in other fields, from the research that they have done in NASA. How go memo? All the young students, you're able to understand. So spin-off, there are many good byproducts from space exploration. So, for example, material for Mars. So in this research, this is from 2019, in this research, NASA scientists, they tried to develop some materials which can be used for the Mars exploration. And that material, they found that they can be used for sutures in the heart surgery and all that. This is a very advanced material. So these are some of the spin-offs. So these are different things from 2019 spin-off annual report. So I'm not going to go into detail, but there are lots in each publication. Understand, Bimo? So if you want to find out about spin-offs, then you can directly go to these different reports. The most important, this is one of the last topics in my presentation, the technology transfer program. I want to highlight a bit. And technology transfer program in any university or research organization is very, very important. I have been to some training on intellectual property sponsored by the Swedish Patent Office in Sweden. I spent about 3 weeks there. So, patent seudalumo, any research organization, when they do certain research, they come out with some very good findings. Now, these findings can have commercial application. If this research has commercial application, the research organization should, or there should be some, process to transfer this technology to the business people. The technology transfer program. So NASA has a very good technology transfer program, and there will be licensing. The researchers should get some share of the money that this business make using that research. So they have such a technology transfer program. I'm not so sure if Royal University of Bhutan has any technology transfer policy or technology transfer program. Mewajin ngache anzum zoni di khache seshuni technology transfer program se labi. So NASA, when they have some good finding, how do they give it to the businesses? They do through this technology transfer program. So NASA gi the technology transfer program nalebe, they transfer it to the businesses. So this is how they do it. They process the new technologies created by NASA, they make it available to the business people so that business people can commercialize it. Commercialization silabongba. Research based how chi product be mitubatemo. Research based how many products zodi gidelidi. So it should be, technology should be transferred through licensing and commercialization. License agreements dobegova ani gidelli. So NASA gi theka bewachin, even you and I can apply for this technology. If you want to, for example, I just did a search online nale wildfires. Did you understand? So during ngigi lecture nale, one takeaway should be the technology transfer program. Technology transfer program, I think, is very important in order to bring these spin-offs into reality, into real life products. So that is actually the end of my lecture. So in closing, I would like to say that space is actually the new frontier now in the 21st century. Most scientists have really pushed boundaries, and now I think next is the space. As human, our human race, they have always been curious about, what lies beyond this and that. So Vasco da Gama and Columbus, they did the exploration. Now we are going to space. Most space, the new frontier, and space spin-offs. So many space spin-offs do more. So NASA Aninalu there is a very nice tagline. They said, there is more space in your life than you think. It's true, most 2000 days. So it is used in the hospitals and everywhere. So that is the end of my presentation. I hope you are able to take away something from my lecture. And thank you so much and have a very good evening.